It is really my pleasure this morning to introduce Dr. Ruthie Halberstadt. Dr. Halberstadt did a bachelor's degree and a master's degree, a bachelor's in civil and environmental engineering with a concentration in earth science, or a minor, both down the road at Rice University, before going to the University of Massachusetts in Amherst for a PhD, where I met Ruthie for the first time 10 years ago. I realized this morning my hair was approximately the same, just a lot less gray. Following her PhD at UMass, she did a postdoc at Berkeley. And as of this fall, she has joined the Department of Earth and Planetary Sciences in the Jackson School of Geosciences, just down the road here at UT Austin. Dr. Halberstadt's research focuses on the processes and interactions impacting the Antarctic ice sheet from millions of years in the past to the present day and into the future. And it really is a privilege to have her here sharing her research with us this morning on integrating numerical modeling with geologic data to understand the Antarctic ice sheet during past warm periods. Help me with welcoming Dr. Halberstadt.
Thanks, Benjamin. Sounds like it's on? Okay, cool. Hi, I'm Ruthie. I'm excited to be here. I'm at the department starting this fall, but hoping to be at UTIG at least every Friday and get to know you all as well. So my research investigates Antarctic ice sheet stability during warm periods, both the past and a little bit into the future. And I use numerical models and geologic data to try to say something, hopefully something greater than the sum of their parts. Why is this important? Why do we care? The Antarctic ice sheet holds a vast amount of water in the form of ice, and when that ice is lost into the oceans, it impacts sea level. So this plot shows projections of future sea level up to the year 2100. The three different bars show three different future climate emission scenarios, and then the bars are colored according to the contributors to sea level. So ice sheets, land water storage, glaciers and ice caps, thermal expansion, all of these contribute to sea level, but Antarctica might very well be the main contributor to sea level by the end of the century. That's this gray bar here. And so this, the future of Antarctica has big impacts on global coastlines. That's what's shown here at the left. This is the centimeters of sea level projected under a future high emission scenario all along the world. And of course, this has cascading implications for people and animals that live along the coast. This is a map of the greater Boston area by the end of the century. I did my PhD at UMass Amherst. And so while I was in Massachusetts, I had the opportunity to be part of a group of scientists and stakeholders that were working together to produce a climate assessment report, including sea level projections. So I was localizing these global sea level projections to the Boston coast. This shows the darkest green colors are the areas predicted to be inundated at high tide, and then the lighter greens are the 10-year and 100-year storm floodplains. And so the point is that a baseline sea level rise leads to flooding, exacerbates storm surges, and has really serious impacts. And my point here today is that when we're thinking about coastal impacts, Antarctica is the elephant in the room, right? Because of its huge potential to contribute to sea level rise. How do we do that? How do we, so Antarctica is the elephant in the room because it's helping us understand past sea level to predict future sea level. And to predict future sea level, I argue that paleo is key. So we use past warm periods to try to understand what will happen in the future. This is my current favorite figure to contextualize and motivate my research. So we'll spend some time here. This plot shows CO2 on a log scale, so higher CO2 is at the top. Age is at the bottom, going from oldest to youngest, a little bit into the future. And the geologic timescale or eras are shown at the top. So this plot of CO2 is compiled from a bunch of different proxies. The oldest ones, like over here, are past indicators of ocean chemistry millions of years ago. And then the last few 100,000 years, we measure CO2 from bubbles and ice cores. And then in the last few decades, this black line, you can measure CO2 directly in the atmosphere. And then we use models of future carbon emission scenarios to predict future CO2. Time periods with high CO2 are also warmer. This is global mean surface temperature from modern, also compiled from a range of different proxy data sets. So you may have noticed that time is not linear, right? You get more and more squished as you go back through time. So we're going to take this plot section by section now. The way this figure works is that this first section shows 60 million years worth of climate evolution, like all squished into this little plot. The Antarctic ice sheet first formed about 30 million years ago at the Eocene-Oligocene boundary. And since the ice sheet formed, the first really past warm period occurred during the mid-Miocene. That's this spike in CO2 here. During the Miocene, they were beech trees in Antarctica. They were vegetation, lakes. I had the opportunity to go and do some sampling in the mid-Miocene. So Antarctica really looked very different than today. Shown for context, here are the future carbon emission scenarios and the corresponding temperature projections. And so you can see that during the mid-Miocene, CO2 was approximately comparable to a future high emission scenario in the next few centuries. The way this figure works is that the most recent part of each section is expanded out into the next section. So we take this little like few million year time blip and expand that out. Now we see the Pliocene. Here, CO2 is approximately modern. This is what we often look to this time period as a modern or future analog. Again, if we take the last few 100,000 years and expand that out, now we see the glacial cycles of the Pleistocene. We see these classic sawtooth shape. And with these glacial cycles, we now see like this is the envelope of climate variability. This is what we talk about in terms of like natural climate variability. And humans first appeared during this time period. Okay, if we expand out this most recent part, now we see the warming out of the last glacial maximum. And finally, this little blip at the end of the segment is the recent measured warming, followed by future projected changes in CO2 and temperature. And so the point of this figure is to place these future projections into context with the past. And the goal is to demonstrate the need for understanding past warm periods as future modern and future analogs. So I've worked on many of these past warm periods. Today, we're mostly going to talk about the Pliocene, and then also maybe a little bit more briefly, I'm going to talk about model data comparison during the last glaciation. First, I'm going to set the stage, make sure we're all on the same page, right? This is Antarctica, the continent, right? These green-brown colors show the seafloor elevation. The blue shows the ice sheet elevation. Much of the ice sheet is touching land at the base. We call this grounded ice. And then the grounding line separates that grounded portion, the ice sheet that's touching the bed, from the floating extension of the ice sheet that we call the ice shelves. During the last glacial maximum, this ice was expanded almost all the way out to the continental shelf edge, and has since retreated to the modern. And so this shelf, when I talk about like the continental shelves of Antarctica, I'm talking about this exposed, this seafloor area here. The ice sheet mostly gains mass by precipitation at its surface. This builds up ice thicknesses of up to 4 kilometers in the interior. And all of that ice gets transported out to the margins where ice mass loss is mostly through calving of icebergs, some melt. The way that interior ice ends up at the margins is generally through these fast-moving corridors of ice flow called ice streams. And they're called ice streams. They form like fluvial-looking flow networks, which I find really beautiful. And just like streams, they converge into really fast-moving ice shelves. These ice shelves are moving ice out to the oceans at speeds of multiple kilometers per year. And so if you're standing there looking at it, you're not necessarily seeing it moving with your eyes, but it certainly changes across days. Now let's look at the actual bed topography under the ice sheet. You can see first that Antarctica is divided into 2 main regions, the West Antarctic Ice Sheet and the East Antarctic Ice Sheet, separated by the Transantarctic Mountains, right? Here they are. They poke out actually out of the ice in a lot of regions. And if we look at the bed topography again, here the greens are bed that's below sea level, so underwater. Well, It's not underwater if it's covered in ice, but it's below sea level. And the browns are land surface that's above sea level. And so you can see that most of the West Antarctic ice sheet and portions here of the East Antarctic ice sheet are sitting on land that's below sea level, significantly below sea level. So the grounding lines might be submerged by a kilometer or so. We call this marine-based ice. We think that marine-based ice is less stable because it's basically sitting in this underwater bowl, right, where the land surface is dipping inward. And we think that these marine-based portions of the ice sheet disintegrated and regrew many times in the past. Okay, so how do we take all of these complex ice sheet processes and represent them in an ice sheet model? Here's a simplified schematic. Here are the main components, right? Here's the ice sheet. Here's the grounded portion of the ice sheet. Here's the grounding line. Here's the floating ice shelf. The Penn State ice sheet model is my primary tool. It represents the thermal and mechanical evolution of ice sheets and ice shelves. A key feature here is that this grounding line is allowed to move so it can respond to the forcings that we apply to the ice sheet. So ice advances and retreats. Some external fields that are input to the ice sheet model include climate, surface climate, so temperature, precip, ocean temperature. And of course, there's a lot of complexity that goes into these systems, and I'm happy to talk about that later if anyone's interested. In my research, I often use climate models to provide that surface climatology to the ice sheet. And the way I do that is usually starting with a global climate model or a GCM. So I start with, say, a set boundary condition like CO2. This climate model has an atmospheric component, an oceanic component. It's got dynamic vegetation, which is pretty cool. So this is a modern GCM run, and it shows all of the vegetation that arises in this model. But it's quite coarse resolution. So here's Antarctica on the GCM grid. And so for my approach, I usually downscale this with a regional climate model to provide that climatology, that temperature and precip to the ice sheet at a higher resolution. Okay, so here we are in the Pliocene, right? Again, this is a modern, often looked to as a modern analog with CO2 similar to today. But just because it has this high CO2 doesn't mean there's not other things happening, right? If we look at this variability across this multi-million year time, there's a lot of variability in terms of CO2 and temperature. So the overall motivation of this work is to understand ice sheet response to warmth. Here we're looking at the past, but of course we're interested in what will happen in the future. So our goal here is to use numerical models and geologic data to try to reconstruct the time evolving or transient behavior of the ice sheet. Numerical models give us spatial context. They replicate the physical processes that we think are important. And geologic data provide the information that's like truth, right? Well, depends on your interpretation. It anchors us to truth in some way. And so we need both of these things to fully investigate ice sheet forcings, ice sheet feedbacks. The tools here are ice sheet models, climate models, as well as the geologic data constraints. I'm going to talk about methods briefly by showing you results. So this is an ice sheet model, a transient ice sheet model, right? It's evolving through time, showing the glacial interglacial cyclicity through the Pliocene. This top plot shows the model forcing, the model inputs. So the purple line is insolation, the orange is CO2 through time. Oh, I didn't label this axis, but it's 1,000 kiloyears, so 4 million years to 2.6 at the Pleistocene transition. And then the bottom plot is the ice sheet response to those forcings, so the ice volume fluctuations. And the way that I've plotted this is in terms of equivalent sea level. So this is how much ice is contributing to sea level. So these spikes are sea level high stands and small ice sheets during interglacials. And this ice sheet is driven by time evolving climate and ocean forcing inputs. The way we do that is with what we call the matrix method. And so I use global climate models downscaled by the regional climate models, right, to provide these snapshots. And these snapshots are static in time, but they form a 3D matrix. So I vary CO2, topography, orbit, that's like Southern Hemisphere insolation. And for each unique set of boundary conditions, I'm creating this climate snapshot. Here's one face of this 3D matrix. So here I vary orbit and topography, and I've plotted the summer surface temperature to show you the variation in climatology. So at each time step, as a model is going through time, each time step in this case is 1 year for 2 million years. The model is saying, okay, like what's the CO2, what's the topography, what's the orbit at each time, and then grabbing the appropriate climatology. Actually, it's interpolating between these. But anyway, it figures out what's the appropriate temperature and precip at each time. Okay, so in this movie, I showed you one model simulation, that's the blue line. For this work, I produced a whole set of simulations. Those are all of these black lines. So each line is one model run through time. And you can see there's a lot of variation, right? Some models have these big sea level spikes and some don't change as much. And so I produced this variation by changing 3 main parameters. Here they are. Again, here's the model ensemble in sea level space. The first parameter I want to talk about is the ice sheet melt sensitivity to the ocean. So given some ocean temperature input, how much does the ice sheet melt at its base in response to the ocean warming, or how much does it refreeze in response to ocean cooling? And so here I've colored each simulation with respect to that parameter. So the blue runs are the ones that are less sensitive to the ocean. The orange ones are more sensitive to ocean temperature. And the goal here is just to show the spread in behavior with respect to each parameter. I also varied the methodology for scaling the climate forcing, which is pretty esoteric. I'm happy to talk about it later if anyone's interested, but basically these are 2 equally physically reasonable methodologies of scaling this climate forcing, but it impacts the results, so I wanted to show you. Okay, and finally, I vary parameters related to hydrofracturing. So this is a hypothesized physical mechanism we think is impactful in warm worlds where there is an abundance of surface melt on the ice sheet. So right now, you know, we think about surface melt in terms of Greenland as being impactful to the glacier mass balance. In Antarctica, it's only really been recently recognized that surface meltwater is even like happening. We think this is mostly a warm world kind of thing that we don't observe today, so it's a little bit controversial. So this schematic illustrates this process. If you have abundant surface meltwater or liquid meltwater, either through surface melt or rain, it can pool into crevasses on the surface of the ice and basically propagate that crevasse through the ice shelf, break up the ice shelf. And then you're left with this sheer cliff face that then fails structurally under its own weight and can lead to large-scale grounding line retreat. It's this positive feedback if you have an inward dipping bed. And so here, these blue lines show the models where this process is turned off. So hydrofracturing is 0. Even if you have a ton of meltwater, you're not going to break up the ice shelf. And red is the max values explored in previous work. So you can see it really impacts the amplitude of these sea level ice stands. Okay, so the goal here with this model ensemble was to simulate a range of behaviors. So that's the first step. Great, we've done that. And now we want to know which one is most reasonable, which one is correct. And for that, we need the geologic record. So I've compiled all of the geologic records I could find that have anything to do with the Pliocene near Antarctica or on Antarctica. And these fall into 3 main categories. First, we have grounding line behavior across the modern continental shelf. Remember, I also identify as a geologist as well as a numerical modeler. So this type of data set is usually seismic records and drill core data. Here's an example of a seismic line on the Ross Sea continental shelf. So here's the shelf break, like ocean, continental shelf, and you can see the bed dips a little bit inwards towards the grounded ice, right? Remember the inward dipping bed is a feature of Antarctica because we have this big loading in the interior of the ice sheet. So anyway, this seismic line is tied to a drill core, so we know kind of what the ages are. We've got an age model. And you can identify these big erosional surfaces across the continental shelf. This is when the ice sheet expanded all the way out to the shelf edge and retreated multiple times in the past. And so we use this type of data to say, how many times did the ice sheet advance across this region and approximately when? Another category of data record the timing and extent of ice mass loss. So this can be ice rafted debris records from a catastrophic ice sheet collapse. And that tells us approximately when and where the ice sheet retreated rapidly in the past. This also, part of this data set can be these marine diatoms that we find in terrestrial outcrops. So that's like a little confusing, right? In this mountain range, this is in Pritz Bay, there are these open marine diatoms, warm water diatoms that we find in this inland mountain range. And so that requires that this region had to be ice-free during that time. And not only no grounded ice, but no ice shelf. And I think probably even no sea ice, but I'm not evaluating that particular component. And then finally, we have some terrestrial data from the Pliocene. This type of data entails cosmogenic nuclide measurements, which I'm going to talk more about later, but basically this tells us how long the rock surface has been exposed to the air, in other words, ice-free, so it gives us an ice thinning history. And this is an outcrop in interior West Antarctica. So here's a summary of all of the geologic data, the marine geologic data that I compiled. So for each major catchment here, I've summarized or synthesized the available geologic data to make some criteria to compare with the models. So that's what these are. This is the criteria that I use to compare, to evaluate the models. Most of these data are seismic records, drill core records that tell us something about the modern continental shelf. And so by definition, that just tells us like what happened with what the ice sheet was like when it was bigger than today. There's a couple of pieces of information about ice sheets that are smaller than today, like this open marine diatoms in the inland outcrops, or there's a key geochemical erosion constraint in Wilkes Land. But we also have some information about smaller than modern ice sheets. Terrestrial records are sparse, worse, equivocal, like, I'm just sort of doing due diligence here, right? But I did look at the terrestrial data. So some cosmogenic nuclide mountaintop data tell us that there were some thickening events during the Pliocene. Some work that I did with Greg Balco during my postdoc takes a transect of cosmogenic nuclide measurements at a mountain peak and tries to recreate the ice cover history. So like how do you get cyclic ice cover and ice retreat at one site? We can only do this at one site, so it's like totally not useful, but again, I'm doing my due diligence here. And then at Andrill, the grains that were eroded and transported to that site have low nuclide concentrations, so we think that probably that catchment region, which is like here, wasn't ice-free during the Pliocene. Okay, so we take all that geologic data, and we can go back to our question of which model simulation is most correct, or which is most geologically consistent. Here's all of the model simulations. The naming convention reflects the parameter combination. And then each column here is a marine catchment or terrestrial data set. And the color reflects, do they agree? So green is consistent, red is inconsistent. And the width of the column shows you how confident I am in that model data interpretation, right? These things, like for example, for the terrestrial data sets, we just don't have good enough confidence in actual terrestrial data to be able to compare them. And there's some other issues with other places. But I guess what I wanted to say about this is it's pretty subjective. Like each model data comparison thing is pretty subjective. But if you put them all together, you start to get a sense of which model simulations actually agree. That being said, reviewer 2 said they wanted them quantified. So, okay. So I put some numbers on the model data agreement and the confidence intervals. And now there's semi-quantitative support for which model simulations are most geologically consistent. So, so these two I'm calling my best fit simulations. And so now that we have two simulations that are most geologically consistent, we can actually query these to try to learn something about Pliocene ice sheet behavior, right? That was the whole point of doing this. This is novel because we have this geologic record of Pliocene ice sheet dynamics, that the actual geologic data are discontinuous in space and time. And so we've taken a model, and basically the way I think about this is we've extrapolated those geologic record into some continuous time evolving ice sheet history. And that means we can get a sea level record or reconstruction. So this is the two best fit model simulations plotted in terms of sea level equivalent. And you can see that they produce these big sea level high stands. So we're looking at 15 or 20 meters above present of sea level contribution from Antarctica. This is independently consistent with the high end of the geologic Pliocene sea. So we have like far field Pliocene sea level reconstructions, which are controversial and hard to, it's a hard field to figure out, right? So this is sort of an independent way of getting at this question of what was the Pliocene sea level. And so this is consistent with the high end estimates of the far field sea level reconstructions. These plots show the two model run grounding lines. And so the grounding lines are colored according to the sea level contribution at each time. And so you can see these high stands are driven by collapse of the West Antarctic ice sheet and portions of the marine-based East Antarctic ice sheet. I wanted to say that, so I'm sort of presenting this as a global sea level record. It's really just the only thing we can do with our models is the sea level contribution from Antarctica. And so if we think about, was there northern hemisphere ice sheet during this time, if Greenland happened to be growing, and if Greenland happened to be growing at exactly the same time Antarctica is shrinking, you could lower these high stands by about 7 meters, which is the sea level equivalent of the full Greenland. That's just sort of like a side note. Okay, I want to point out something interesting, which is, I think is interesting, I hope you do, which is if we zoom into some of these glacial cycles, we actually see a sawtooth pattern, which is super cool. So this is because we're using a physically based ice sheet model. We get rapid retreat, slow growth, rapid retreat. The growth happens when you cool the oceans, that maybe an ice shelf grows out into the oceans, it thickens, it pins on bedrock highs or banks, it starts to coalesce, and it creates a grounded ice sheet. And then you get deglaciation when you warming hits some sort of threshold, and then these instability feedbacks kick in. This includes the hydrofracturing parameterizations, but isn't limited to. So this is sort of a classic feature of ice sheets, and we can see this in the model. If we look at this another way, so here I've plotted the rate of sea level change at each time step, and the dots, the color and the shape of the dots are the rate of sea level change. And now instead of doing that through time, if we plot it with respect to the ocean temperature anomaly in the model, now we can start to think about thresholds. So here, this axis is the same as the top sea level equivalent. Here's the ocean temperature anomaly. The way to look at this plot is like, say we're starting off here. We have a big ice sheet, and the dots are small and blue. Nothing really is changing. You're warming, you're warming, you're warming. And all of a sudden, maybe you start to retreat a little, and then boom, you hit this threshold. And now you've got these yellow deglacial episodes, right? So then you're shot up here into this space. You have a tiny ice sheet, high sea level. As ocean temperatures cool, you kind of grow slowly, somewhat linearly back into a big ice sheet. This is a 1.5 degrees Celsius threshold. This absolute number is somewhat dependent on the model experimental setup, but it's still, I think, a big yikes moment, right? That around 1.5 degrees warming, you trigger these big sea level responses. So this, again, these sea level high stands are driven by West Antarctic ice sheet collapse, East Antarctic marine basins. This is kind of, this is actually dominated the signal by the East Antarctic because, this is sort of a bigger area, but East Antarctica is this big, thick ice sheet. And so when you start taking these cookie bites out of it, you have to thin a ton to get the grounding line to retreat. And so you actually contribute a lot of sea level from the East Antarctic ice sheet. We talk a lot about West Antarctica, West Antarctic ice sheet stability. And so I wanted to look at just West Antarctica. Now I'm plotting just the West Antarctic ice sheet contribution to sea level here on this axis. So you can goes up to 5 meters above present rather than 20. And now you can see the threshold for collapse, that's where these yellow dots start happening, is much lower. So it's about 0.5 degrees Celsius, and the threshold seems to be quite a bit more complex than East Antarctica. And so this is sort of supporting our understanding of the West Antarctic ice sheet as the system that is pretty sensitive. So what can we learn from this work? The two most geologically consistent model simulations are showing rapid episodes of ice sheet collapse, large sea level high stands in the past, and the thresholds for these collapse events are not too far off in the future. And this work was recently published with old collaborators and new. This is my PhD advisor and other folks I met along the way. Okay, that's the Pliocene. Now we're headed into another warm period, or another warming period, right? The last deglaciation. The amplitude of warming during the last deglaciation wasn't quite as extreme as like a past warm period, or really analogous to the future. So like, what am I doing here? But actually, this is a really key time period because it's when we have the most data, right? So we look to this time period as a test bed for understanding ice sheet behavior, understanding stability. Look at all this data. So this plot shows all of the geologic data that record ice sheet thinning. From the blues are the terrestrial age dates that record ice sheet thinning. The yellows are the marine data that show ice sheet retreat, grounding line retreat. And with this wealth of data, we now have all this key information, but we run into another problem. We have so much data, we have another problem, which is that the different data types don't actually agree. So if you're an exposure age scientist and you're like, I'm going to build a picture of Antarctic deglaciation from these exposure ages, you get like a different picture than a marine scientist. And the communities aren't always really talking. So that leads to another problem. But for example, terrestrial ages suggest that there was a rapid ice sheet thinning sort of late in the Holocene. But the marine ages show sort of grounding line retreat 2,000 or 3,000 years earlier. So that doesn't make a lot of sense. And so the assimilation and interpretation of these different types of data sets is preventing us from getting a big picture. And that's important because we need a consistent picture of, or consistent history, ideally a model history of Antarctic deglaciation to reconstruct Antarctica's contribution to sea level, to deglacial sea level rise, like the timing, the amount, the source, right? Where Antarctica loses mass actually changes the fingerprint of sea level all around the globe. So this is really important to get this right. And we also need a spatial and temporal unloading history to inform Earth models, glacial isostatic models like Keisling, like the work that she does relies on these loading histories. And so we need to be able to get this right. To do this, we use numerical ice sheet models, right? We use the marine and terrestrial data sets there and an ensemble of simulations with different parameters that we can then score to try to figure this out. But this is still a work in progress, so I don't have any nice, neat answers wrapped up today, but maybe next year. Okay, what are these different types of data sets that we use to reconstruct deglacial behavior? First, we're back to cosmogenic nuclides, same photo. These terrestrial exposure ages, basically we use mountain peaks that stick up out of the ice as like a dipstick. You check your oil, right? Like you see the level of oil. So it's a dipstick to record ice sheet deflation through time. And this works because as a rock surface is exposed to the air, the cosmic rays interact with the quartz minerals in that rock. They build up rare nuclides. And so we measure cosmogenic nuclides to tell us how long that surface has been exposed to cosmic rays. In other words, how long it's been ice-free. So, for example, at this outcrop, say the tip of this mountain was exposed during the last glacial maximum. So these samples would have really old ages, maybe millions of years, maybe Pliocene. But anyway, older than the last glacial maximum. And then as the ice sheet thinned, the ages along this elevation transect get progressively younger. And so we can use this to record the extent, well, the thickness and timing of ice sheet thinning. And that's a model quantity. So that's what we use to compare to the models. This work is done in collaboration with Greg Balco, who was my postdoc supervisor. And he's an expert in cosmogenic nuclides. This is like a new field for me. This is what I learned about during my postdoc. If we look at marine data, these don't tell us the thickness change of the ice, but they tell us the spatial change of the ice. So we can do this by surveying and coring the modern continental shelf seafloor. This is especially fun for me because this is where I started off my Antarctic journey during my master's, was surveying the Ross Sea landforms of glacial retreat and then linking those together to map the grounding line behavior across the continental shelf. So here in blue is the last glacial maximum grounding line position. The ice sheet shrank, pinned on banks, eventually retreated to the modern configuration. So we actually sampled the seafloor sediments to get the actual retreat age. This is a schematic by Prothero et al. Showing the glacial depositional environments. And the key piece here is that here's the grounding line. We get this basal meltout zone that stays close to the grounding line. This has a unique sedimentological signature, and we can identify this in marine cores going through the past, age date these samples, and that tells us when the grounding line retreated across that site. We're also interested in open marine sediments. These are a lot easier to identify in cores. They're a lot easier to age date, not so useful for models, right? It gives us a minimum age of deglaciation. It doesn't actually tell you when the grounding line passed, just that it has already passed. And this is in collaboration with Ryan Venturelli and Lindsay Prothero, who are marine geologists. So my job is to take all of these data, these marine data, the terrestrial data, they're recording different things. They have different strengths and weaknesses, and try to make some sense of this in a model evaluation framework in a way that makes sense. Right? Like this has been done before, but it hasn't been done using all of the data that we have because there's such a difference in quality between these data sets. Usually people curate it. So you grab all the data, one person grabs all the data, says like, I'm going to use that constraint and that constraint, and then ranks your model based on that. The problem with that is that there's maybe some user bias. It's not always clear why different dates were chosen. And you don't use all of the data that we have. And another problem is as soon as somebody goes out and collects more data, it becomes obsolete pretty quickly. So our goal is to try to put this all together in an automated framework using all the data. And here it's a lot of nitty gritty. The devil is in the details. Here's one example. So this is all I'm going to show, and then I'll move on. But here's one example of terrestrial model data scoring. So here you have one exposure age site. Each green dot is the exposure age. It's along an elevation transect, right, a mountain peak, and the uncertainty is here. And then the black line is a model thinning curve. And so for each sample at this site, we identify what is the time difference between the age at that elevation that was measured and the time that the ice sheet reached that elevation in the model. This time difference, along with uncertainty, gets into a squared error that gets summed. You get a site score, and then you combine that to get a model score, and then you can start evaluating things. So so part of this work is to create a public model data comparison toolkit. And so here, anyone who's got an exposure age site they're interested in can type it in, choose what model simulations to plot, and figure out which one best matches their site. And so I'm excited about this because it means that researchers can say, you know, what's happening? Like I've measured this thinning, like what's happening? What's happening spatially? And so you can grab a model simulation and look at like what process is even causing this thinning that you're seeing in your data. So then I also wanted to say, one big issue that's hampered this kind of thing in the past is that, especially for exposure ages, right, they're collected on mountaintops, almost by definition. And mountainous areas are complex. They're high resolution topography, like the Transantarctic Mountains. And if you're modeling, which you sort of are computationally limited in your model resolution, if you have like a 40-kilometer or 20-kilometer model, continent-wide model that's going across 20,000 years, your grid is like 40 kilometers by 40 kilometers, right? That's not going to resolve a lot of this complex topography. And so one of the things we're doing in this project is I've run a bunch of continental scale models, sort of classic approach, and then I've downscaled each location where there are exposure age dates. I've downscaled into a 2-kilometer by 2-kilometer resolution postage stamp that's driven by those boundary conditions everywhere across the continent to try to replicate this thinning in a way that actually resolves the relevant environments like the trough, the mountain peak. And so far we've demonstrated this actually really improves model day agreement. So like, great, this is a proof of concept. These are two different metrics for scoring terrestrial data. This one is how the amplitude of thinning, like how much do the models thin since the last glacial maximum, and how does that agree with the data? And this is just sort of the shape of the thinning curve. And so here I've plotted each model run twice. The diamonds are the continent-wide model, and then the circles are scoring that same model but downscaled in these little postage stamps. And so this seems intuitive, right? But it's the proof of concept that when you downscale a model to a high resolution before even trying to compare the modeled thinning history with the observed thinning history, you do a lot better, right? We're actually resolving the glacial environments that occur. So now that I've got this framework, the public tool, all of that's getting published soon, hopefully, and then I can actually apply it to start reconciling these marine and terrestrial data. So stay tuned. Coming back full circle, my main point today is that Antarctica is hugely impactful to global coastlines. And so therefore, we should all care about Antarctica. Like the fate of Antarctica is key for understanding what is going to happen to future sea level. And furthermore, paleo matters. Reconstructing past warm periods is really key for being able to understand and project what will happen in the future. As a reminder, here are the 2 time periods I talked about today, but I also want to point out I worked on lots of other past warm periods and would love to talk about any of these projects. This one is the mid-Miocene, reconstructing ice sheets and climate temperatures, ice sheet configurations in mid-Miocene. If anybody went to my job talk like 2 years ago and has an excellent memory, I talked about this as well as landscape stability in the dry valleys. I've also worked on remote sensing of surface meltwater and how that relates to hydrofracturing in the satellite era, so the like modern warm period, as well as a little bit of future sea level projections. Okay, that's it. Thank you.
Wonderful. Questions for Ruthie? And we will start with a question from any students that might have a question before. Yeah, Ed, let's start with Ed.
Thanks, that was really, really interesting. I was wondering if like your climate model inputs also evolve through time, because I guess you've got this 2 million year period, and I can imagine that like a lot of climate changes in that period, and also whether it's sort of tied to the plate reconstructions, because I imagine that closing North and South America also might have a climate impact. So
yeah, thank you. So well, for the Pliocene, we're not super worried about tectonic movements, which is another reason why it's been a focus of the global community, is because all of the ocean gateways were open by then. And so we're like, not so worried. For the Miocene, that's a different story. But it would be great to have a coupled ice ocean climate model. We don't have that right now. And so this is, the matrix method is like a crude approximation. And so the goal of that is to, obviously, you have different climate states at different CO2s, but the reason that we've used different topographies is because of what you're saying, like as the ice sheet is moving, as retreating and expanding, that changes the local wind patterns and the local precip and the local temperatures. And so that's like one way we're trying to get around that question. For the Miocene project, we can use paleotopography that re-rotates the continent based on how we think that the plate tectonics were changing, as well as the global climate model has the paleotopography. Yeah.
Torsten had a question.
So for the Pliocene, it seemed like the constraints demanded a large amplitude response from the ice model. Now, presumably that's not just some linear sensitivity, but some feedback process that amplifies that. And I think you mentioned hydrofracturing and things like this. So I was wondering if you could comment on what do you think the robust ingredient in these models is that seems to be required by the geological constraints? Is it this hydrofracturing or is it something else?
So one of the motivations for this work at all and burying the hydrofracturing was because it's really tough to find any kind of geologic constraint for this process. So what you've asked is, like what in the model is controlling that behavior, and hydrofracturing is, and so that's why we've developed this angle. The ocean melt sensitivity also controls that to some degree. But what I've attempted to do is try to be like model process agnostic in here and say like, look, I don't care what you think about hydrofracturing. I don't care what you think about like ocean melt sensitivity or the various, tweaks in the model. The point is to extrapolate the geologic record. And so that's, to what degree that's philosophically possible or not can be debated, but that was how I went about thinking about this, is like, okay, the geologic data demand these large scale changes. Here's a couple of knobs I know that can get at it. And so like whether or not we're turning the right knobs, like you could do hydrofracturing, you could do other kinds of grounding line tweaks that other folks have used to create this kind of dynamic thing. And in the end, it's just parameterizations that by nature aren't reflecting the real behavior of an ice sheet, because that's a parameterization. And so I'm sort of wiggling around that question because
But if you don't want to narrow that down, then what's the point?
the point is to get the sea level. The point is to say,
Right, so but we know that there's this large thing, so we need a model that has these large amplitude fluctuations. Can't you
right.
then take it one step further and see which sort of process that might bring?
Yeah.
Because then I don't quite understand.
yeah, well, I mean, so we can't, so there's like, I think 2 points of interest. One is for the modelers, which is that question is like, what does that mean about how physically realistic these parameters are? And we have said like, you need a medium to high amplitude of hydrofracturing to get, and so we've provided that. But I think that the real impact of this work is saying, okay, you see continental shelf expansion and you see retreat that's at least this much, but not quite this much in the geologic record. What does that mean for sea level? And that's where I see the I guess more impact of the work.
Thanks. Really awesome talk. I've got lots of questions, but I'll just confine myself to one. The bed topography and erosion of the Pliocene, is that a significant factor, or?
We don't know because we haven't modeled it.
Okay.
Like the model doesn't have landscape change, which is on a wish list, but probably lower than ocean coupling.
Okay, fair enough.
Other questions for Ruthie while y'all ponder? And if there's any online, we can take questions from online. But I was wondering, Ruthie, I really liked this amplitude versus forcing plot that you showed, this question about hysteresis, and you sort of I was wondering if you can say anything about rates of sea level change in the past. You mentioned that there was a sort of asymmetry in between deglaciation and glaciation. And then when I look at the rates of deglaciation, it looks like, 4,000 to 6,000 years, you're changing sea level by 20 meters. It's sort of in the 5 millimeters per year, like long term. But I was wondering if you see faster rates of sea level change transiently, and what you think this work implies for the sea level rates that might be possible in our future.
Yeah, I think that's one way of making that plot with the threshold for deglaciation and making it even scarier. So I didn't do that, but totally could. The biggest, I forget exactly, well, I won't go all the way back, but I think the biggest rates were on that order. It was in millimeters per year. I think it was up to 3 or 4, but yeah, I could look. I mean, the other thing about that is that the rates are somewhat dependent on the parameterization, but again, we're like trying to back out the parameterization from this work. So we should make that plot.
Yeah, Jeannie.
Sort of along the same lines for that threshold plot. I was wondering how much stake to put in the actual ocean temperature and more thinking about there is a temperature that is above 0 that matters for melting, but then the topography and how steep that bed topography might be could control the rate of retreat that's actually happening instead of it getting to a certain temperature for different parts of the ice sheet.
Yeah, I think that's why. So the reason, so the like full ice sheet with the clear 1.5 degrees Celsius temperature threshold, that's East Antarctic dominated. And then we looked at the West Antarctic one, which is a lot messier. And I think that reason is why the West Antarctic threshold is not like a clear threshold is because there are lots of other complicating factors like bed topography, initial conditions, things like that. And the reason the East Antarctic one is so stark is because it's mostly driven by hydrofracturing of those marine basins. And so that parameter, that process has like a clear trigger. And that's why you get that clear deglaciation response. But I think that, yeah, those other factors. And I tried a little to see if I could tease out some of the other modifiers of that threshold, like bed topography and CO2 as well, with not as exciting results.
We have a question from online and then Kaishwan. Sure, Kaishwan, go ahead.
Really good talk. Yeah, I just talk more about those thresholds about the West Antarctic collapse. You followed by Jenny's question. So you mentioned for the West Antarctic the threshold for the temperature 0.5 degree. So what can we learn from this Pleistocene collapse? So when we just when we have those temperature warming, so if we just pass this threshold, the whole West Arctic ice sheet will collapse, and or it will just fluctuate. Fluctuation just multiple retreat and flex multiple just second order phase due to the temperature fluctuation.
Yeah, that's an interesting question. I think, I mean, we sort of one thing that we know about large scale ice sheet retreat is that it's a lot easier to retreat it than regrow it. And so it wouldn't be, what's the word? I forget. Anyway, it wouldn't take the same amplitude of negative forcing, in other words, to get the ice sheet to re-advance. But yeah, that 0.5 degrees Celsius threshold doesn't mean like you get 0.5 degrees and you retreat. You might trigger that earlier, a little bit later, based on other factors, which is why like those dots were all kind of mixed in around that sort of temperature band. Yeah, sorry. Was there another part of the question that I missed? I got excited about that.
All those little fluctuation. I mean, the first order of those ice sheet collapse maybe just highly correlated with temperature. But for those
I see.
little, small fluctuation, maybe we can just consider kind of second order, like the bedrock evolution.
So yeah, one way to think about that is, so the ice sheet model was run time evolving through about 2 million years. So I output like model results. So the model computes at least every year, but I save the model run, like it outputs the model fields every 2,000 years. And so each time step is every 2,000 years. And so that's sort of a computational constraint, but it prevents us from looking at processes that might drive grounding line fluctuations. I think the kinds of things that you're thinking about are probably faster fluctuations driven by, maybe climate variability, ocean variability, maybe some sort of internal thing. And so we could run for one glacial cycle and output every 100 years and look at that. But that plot that I showed probably is just showing the first order effects. Yeah.
Take one question from online. If you could throw the microphone back to Constantina. Thank you.
Thank you. So Daniela Tuma asks, have you compared your results with a fully coupled Earth system model? How do CMIP style models do with Antarctic melt compared to your model?
Yeah, so nobody yet has asked about the ocean, how I scaled the ocean, which is like a lot of hand waving, but that hand waving was informed by looking at CMIP. So MIP is model intercomparison, and CMIP, I guess, is climate. But anyway, I was looking at the paleo. So there's Pliocene model intercomparison projects, and other sort of paleo coupled models. And so I was able to basically look at how the coupled ocean responds to the climate forcing and then build some kind of relationship to scale a modern ocean. And so that relationship is like somewhat baked in here in terms of how the ocean and the atmosphere behave together. In terms of how the ice melt changes everything, the answer is it probably does, and no one has been able to look at that yet, with one exception. And this is because, like in all of the model intercomparison stuff, there's so much computational limitations. You have to be really careful about what kind of questions you're asking. And in general, people are asking questions about how the ocean and atmosphere respond, or how, what's the latitudinal temperature gradient, things like large scale global features. And so because of that, the ice sheets are always fixed. So not only do they not change their, like if you had a really warm climate, you would have the same ice sheet as a cold climate. You're not growing or expanding ice sheet, growing or shrinking ice sheet. So not only do you not change the configuration, you also don't change the local oceanography or the ice melt or the sea level. So that's a big computational weakness in our understanding of past climates. The one exception was a colleague of Benjamin and myself, Shana Sadai, coupled our ice sheet model with all of the meltwater forcings and looked at how that changed global oceans in CESM. And the answer is it really does, like big surprise. So that's a frontier.
Wonderful. Ruthie has quite a full schedule this afternoon, meeting with folks here at UTIG, but I want to highlight that she will be here most Fridays. So if you don't get a chance to talk to her today, definitely reach out. Any students that want to join and postdocs for lunch, we'll gather in the main area at 11:45. And if anyone wants to join Ruthie and I for dinner tonight in Hyde Park, just come let me know. With that, let's thank Ruthie again for a wonderful talk. Thanks, Ruthie.